because that annoys me for the whole time, the first talk. Oh, I can have moderators. What's it need to do? Like, what is it doing while it loads the thing? What's it doing? Oh, there we go. Okay, that's me. So close that now. And then the slide.
It's Ubuntu based or
this is Windows.
Windows.
Yeah, this is a University of Birmingham official machine.
That's always a mistake too. So.
Yeah, but I'd rather have something that's plugged into everything than having to try and fiddle about with all the. Especially if you're using a Ubuntu thing or Linux thing, you need to try and put your HDMI in, it doesn't amplify properly, the sound doesn't work.
That's the growing pains.
Right, no enforcement, there we go. And I'm going to hide the mute controls. We are unmuted. It's very good. Hide controls, that's in. Oh, we have 4 minutes left anyway. Then this is going to work. And this should just.
Can I check the equipment?
Yep, sure.
So, yeah, it's just. Okay, down goes forward.
Paul, would you like to do the horn to make him? Not yet. We've got 3 minutes.
Wow. So what does this do?
I have no idea what that does.
But it doesn't break anything.
Yeah.
It doesn't break.
Yeah, I have no idea what that button does. It makes a little light flash. What's that mean?
Is that for like the laser?
No, the laser one's the one
Laser
further down. So I have no idea what that top button is. That's just
Maybe it's
part
just to make some light.
Yeah, to show you it's working, I guess. Yeah. I don't know.
Maybe if I keep it in.
Oh. It's like an old. Oh no! You found the exploit. You've got root access now. So you've got root access. No. And I assume. Oh yeah, that's just again the last check. Share. Not live stream. So I'm recording. Cool. We're recording. Oops, sorry. Back. Yeah. Don't. Oh, I did not do what I wanted to do.
Do you have
As it should be online. I don't know if he's here now.
Okay.
Only I am here now. Just George K. He should be online. I guess if he doesn't turn up,
Has he sent you slides?
No, he's not.
That's fine.
But that should be fine actually. This is the one time that's fine.
Yeah.
If he doesn't turn up, well, I guess we proceed to the next talk.
You've got all the other slides.
Yeah. So yeah, and I will tab over to the next one after that's done. That's done. That's fine. I'm in. All nearly there.
My watch is about 75. My watch says about 197. Yours says 30. Okay, right. Okay. Hello everyone, welcome to the late afternoon session. We're starting with David Forsberg from Louvain, who's going to speak to us about a monoidal meta theorem.
Hey, first of all, I want to thank the organizers and the people who got me here to talk. So I appreciate that. And so a couple of months ago, I believe I proved this theorem, so I would like to explain what it's all about. So a monodal meta theorem. The meta theorem here refers to the idea that you prove something in sets and it should generalize into all monoidal categories. So, so the question is, of course, this doesn't hold in general, but in some settings it does work. So the talk will be kind of partitioned in these 4 parts. First, I will introduce a little bit, talk about coherence theorems, define the universal algebra setting of the algebraic theories, and then I will prove soundness and completeness, and this will encapsulate the method. Okay, so this is the formulation. So if I have what I call monodal theory, Cartesian theory of symmetric monodal theory, and I assume this is such, then I will have this kind of property that if these equations in sets, or so all models of this theory E is satisfied by a model, then the model satisfies this. So this is what it means that this phi is logically entailed by E, and then it implies that this is logically entailed in an arbitrary monodal category, symmetric monodal category, or Cartesian monodal category. Okay, so let's look at an example. So the Ekman-Hilton argument, we fix 2 unital magmas. So we have 2 binary operators, 2 nullary operators. We set the theory of these being, I think there should be, this should, okay, that's, okay, either way, think about 2 unital magmas, and then there's the interchange law. I think there's a mistake here. And then in sets, what does it imply? It implies that if you have a model satisfying these axioms, then you will actually have an abelian monoid, and these 2 operations will be the same. So that's the Ekman-Hilton argument. And so what does the monodal meta theorem have to say? It says that then this should generalize to all symmetric monodal categories. And why not monoidal? Why symmetric? It's because there's 2 variables over here. They change position. So the z and y have changed positions. So therefore, this is not. We are not able to interpret these equations in a monoidal category. But because they have the exact same variables, only up to the position is up to permutation, this will be able. We are able to interpret this in any symmetric monodal category, and this will be meaningful. That's okay. So non-examples. So what cannot be lived from sets to arbitrary monodal category? So if you fix a signature with the single sorted signature, we fix 2 function symbols to the empty word. Then in sets, this will be interpreted as a terminal object, and therefore any 2. If you have a model, then this will be can prove that this will be true that these are equal in sets, because any 2 morphisms to the terminal object will be equal. But in the setting of abelian monodal category, this will not be true. Think about the tensor product and the unit being the integers. So we have multiple homomorphisms on z to itself. So, for example, so this is not true. So this kind of theorem cannot be lifted, or statement cannot be lifted from the sets to the arbitrary monodal category. And then there's a second counter example of non-example. So if we have this kind of so this would be an example of a signature that is not sort value, it's a kind of type value. So we fix a single sorted setting. We fix 2 function symbols that have a domain like that, and codomain is kind of product. Then we fix a theory that says that these 2 things should commute. And now in sets, what happens is that we can prove that they have to be equal. We can project this by the 3rd projection, and then we get that the f and g are equal in the 2nd projection. Here we get that f and g have to be equal in the 1st projection, and therefore f and g have to be equal when they're modeled in sets. But this is not true in that setting. In the setting of the opposite category of sets equipped with its co-Cartesian structure. So we can give an example of a model where this is not true. So this is kind of when we have a codomain of these function symbols that is not a sort, it's this kind of a word. Then we are not able to leave this kind of theorems. So what kind of theorems can we? So first, I will talk about the definition of a monodal category and symmetric. So we say that this is a magma. So we have a magma structure on a category pointed magma structure. We have some object, some binary bifunctor, and then we consider different kind of natural transformations. This one is called an associator. If it's of this form, left uniter, right uniter, symmetro operating, a deleter. I'm not sure if this is standard or not, but I remember hearing it sometimes. Could be. So it's supposed to be the unique map to the terminal. And then we have the diagonal. So if we have the first three satisfying coherence axioms, we have a monodal category, we have a braiding satisfying with the first four satisfying suitable axioms. We have a symmetric monodal, braided monodal category, depending on your coherence axioms. Then we have this deleter, if it has it as the suitable coherence axiom, it will just give you that this has to be the terminal object. And then we have, if we have the all satisfying suitable coherence axiom, we have a Cartesian monodal category, which is the same as having diagonal projections, which can be constructed from this data. You use this tensor product is with y, and you use left or right uniters, you will get projection models out of it. And if you have the compatibility with the diagonal, you will have the Cartesian structure of Cartesian monodal category. Okay. So, to define the language, I will quickly just talk about a free monoid and a pointed magma. So free monoid is all the possible words that you get from a set. So you have this disjoint union, and you have this, you can measure the length of each word. Free pointed magma is without any, it's kind of the free monoid without any axioms. So it's defined recursively. So for any letter, any element of X is considered an element, and then we have some kind of points that we choose, and then we can concatenate with brackets. This recursion defines you a free pointed magma, and then we have we can remove brackets. So we have this kind of function, and then we can add brackets, right bracketing. We can add, and then we get from words of this form from the free monoid over this set we get mapping there, which will be a section down. So which I call a right bracket. And for each word or for each element of the free-pointed magma V, we are able to define those indices at which point this is not a trivial element. So that I would call them the essential indices of a word V, or this kind of bracketed word or non-associative word. And here's an example. If X is an element set of two elements, then we can have this kind of word here, bracketed word, and then we have the essential indices are the positions in which E does not appear, and then the non-bracketed versions. Okay. So now I will talk about. This is all about the coherence theorems to formulate in this neat way. So we want to define the Cartesian monodal completion of a small category. So we fix a small category I, and then we want to define a new categorical structure that gives it products in not in the sense. So we will see in which sense it will give it the products. So the objects are just the parenthesized words of I, of the objects of I. Then a morphism between two of these words consists of this pair that maps the essential indices from here to there, and such that you have these morphisms accompanied. So there's a good intuition why this has to be the case. and it's easy to compose it. Okay, so this will have a Cartesian monodal structure. You can check that it has the binary products of terminal objects. Terminal object will be, of course, the E that I mentioned. So, and then it has two wide subcategories. I would call a symmetric monodal completion I and the monodal completion I. And actually, to prove that these are the monodal completion or symmetric monodal completion is exactly a coherence theorem. That is what that's a different way to encapsulate the coherence of, let's say, symmetric monodal categories or the monodal. Okay, so the relevant coherence. So these have the correct structures, and if we have a functor from I to the underlying category of C, where C is this kind of Cartesian symmetric monodal category, then there exists a unique extension. So this will encode the whole coherence. And there's an extra condition that gives you more cumulative diagrams. But for sake of time, I need to. Okay, so so then the idea is that so we can, if we are given the evaluation functor, we can use the transposition, the exponential transposition, and then we can. This will always have the same structure as C point-wise, so we can use the universal property extent. So each morphism here can be considered a natural transformation. So there's an example. Okay. Okay. So here is the basic universal algebra. So that was to kind of talk about the coherence theorems, and the reason why it's important is that the most difficult job of this meta theorem is to prove that it is sound with respect to any monodal category, any symmetric monodal category, and that's where the coherence theorems become hugely important, because you need to know how to handle the coherence theorems, otherwise the soundness theorem is that you will not be able to prove it, or it will be very, very difficult. So you need to have a handle on the coherence. So that first one part was to recapitulate the coherence theorem in this interesting way. We will use it later on if I have the time. Okay, so I will talk about the signature of universal algebra. So this will be multi-sorted. So we have a set of sorts, then we have a set of morphism symbols, and each morphism symbol is associated with arity and a co-arity. And the arity will be this kind of word of sorts, which is called type, and then it has a codomain, which is a sort. So it's a sort value in some sense. And then each, where we are equipped with variable symbols V with typing, so each variable symbol is given associated with sort, and such that for each sort we have counted the many variables. So 5 is going to be. And then we usually denote signature as this pair of sorts and morphism symbols, or sorts and morphism symbols and the variables. The variables are kind of implicit. So we have this notation that X is of type S, means that the image of X is S. And we use this kind of notation. And if this is the empty sequence, the domain of the morphism symbol is empty, then we call it a constant symbol, and we know it is a symbol of type B. Okay. So what is a model in a monodal category? So so if we fix a signature and see any monodal category, then we can talk about the sigma model in C. So it associates each sort with an object, and then each morphism symbol is associated with a morphism in such a way that this will have this kind of a domain. So this just means that we have a word, we right bracket the word, and so we put the brackets to the right, and then we use we extend this to the unique morphism of the pointed magma. So makes sense. And now then so this is a model, and a model morphism is just we have two models courses of this family of morphisms such that this kind of a diagram commutes. So it kind of looks like natural. Then you can see that there is this kind of functorial semantic business going on, and this connects to Lavier theories and so on. But and I think this monodal setting there will be a connection to Lavier theories, but it doesn't. You need to kind of restrict a bit. You cannot take the category with products. You have to have a category with monodal structure. Okay, but by the way, let's come. So what is a term? So each variable of a constant symbol is a term, and then the type is preserved. So we define terms with a typing. So the atomic terms are just constants and variable symbols, and then we use the function symbols to create more terms. And then for each term, you can find the underlying sequence of variables. So this is how we define it. So each term has some variables, and then we choose the variables expressed in the term, and we have a word. So now we define a context. So an element. So if a B is the set of variables, so we take an element of words of this. So we take a word of variables. It might be an empty word. So we call it a context if no variable repeats it. So no variable, okay. And then we say that it's the context is a Cartesian monodal context, or just a context for a term if all variables in T are expressed in T. And then we say it's a symmetric monodal context if the variables underlying T is a permutation. So no variable is allowed to be expressed twice in this term. So we say that permutation of this. So then we say that it's a symmetric monodal context. And if the variables are exactly in the same order in the term as in the word, then we say that this is a monodal context. And this is important for us to define monodal theory. And then we say that a term is a monodal term if this is a context, so meaning that no variable repeats twice. So constants, you can have multiple constants in a given term, but the point is that no variable shall repeat twice, then we call it a monodal term. And also the thing is that we can construct these monodal terms recursively. So we can prove inductively things about these monodal terms, and we construct make recursive construction of them. So that's actually important technical detail. Okay, so theories of universal algebra. So first we just fix a signature. We have these two terms. If the two terms of the same type, we call this a sigma equation. A set of these sigma equations is called a sigma theory. And we say that the equation is symmetric monoidal if they have a common, this kind of symmetric monoidal context or monoidal context. So saying that if all variables appearing here are appearing here and no variables appearing twice in either side, so if they share the same the variable sets of these two are the same and no variable appears twice, it's a symmetric monoidal equation. And then I would say it's a monoidal equation if they have this exact same variables in the same order and no variable appearing twice. So this is what would be a monoidal equation. And then a set of these will be a symmetric monoidal theory or just a monoidal. Okay. And now we're using the coherence theorem to define so-called canonical modes. So if you have a sigma model in a monoidal category C, notice that typing defines a function to sorts, and the model itself defines a function to objects. So therefore, we can extend it. We can get this kind of strict free functor as strict functor. So this is the free monoidal category, free symmetric monoidal category, or free free Cartesian monoidal category, but that we defined earlier. I use different notation, but we can get this from this information we attain this y for the universal property. And then if we have a contexts, so now these are not words, they are bracketed words, but the same definition. So if this is a context for that, then we can define, so this means that all the variables appear in here, and no variable appears here twice. We are able to define a morphism between these two objects, and it's a unique morphism from B to W that exists here. We can show because there's no variable appearing here twice, and all variables here appear here, so therefore there will exist a morphism, and this would be unique in this category. So therefore, we can specify exactly say kind of morphism here. This would be a canonical morphism. It can be a projection, it can be a diagonal, it can be associated or something like that, depending on the structure of the words themselves. So this is, to define this requires a coherence. So that's the whole thought. Okay. So we call this the canonical morphism. Okay. So now we are able to define this for each term, and in a context, we are able to define a morphism in a monodal category or a symmetric monodal. So if this V is a context of that one, we are able to define a morphism in that. So if T is a constant, we can just project all the extra stuff out, and notice that if we are in a symmetric monodal setting, V is only some kind of parenthesized words of these unique objects. It's nothing else can be there. Otherwise, it would not be a context for the constant. So we just use the left and right uniters as many times as we want here, and we will have a unique morphism. That one for the coherence theorems, and then we use that because it's a constant, it becomes a morphism. Yeah. Then if T is a variable symbol, we are able to define this kind of morphism, and then the recursive step where if T is constructed like that, we are able to define the MD of T as such. And this works. And now this is where we have to be careful to look that all the things work out. Because this is a crucial step that this kind of recursion works. You have to check that everything works out, and it does. So therefore, you are able to define for each term that you have, you can gain a morphism. If you are given a context for this term, then you are able to construct a morphism in the monodal category or a symmetric monodal. So this has to be the correct context. But yeah, okay. So there's this kind of a context independent. So this is the important stuff. So if we have two contexts, different contexts, so it means like two different parameterization or different permutations, and this equation holds, then it will hold in the second context too. But this is an if and only if thing if this is this volatile like symmetric monodal context. But if the context is just this Cartesian context is just arbitrary, then we don't have independence of context. So therefore, your equations in if you want to model your in a Cartesian monodal category, you will have your equations will have this dependence of context, because you can choose different amount of variables for your equations, and if one equation has kind of more variables in the context, the morphisms will be different, and therefore your meaning will be changed. So the choice of context is actually critical in the case of Cartesian monodal context, but there's this kind of a context independence here if we are in the setting of symmetric monodal or monodal category. So therefore, these equations are meaningful so they are independent context. But the context is very important in determining equations in the Cartesian. Think about sets with that models are allowed to be empty sets. So that's so usually you model universal algebra with non-empty sets. But if you want to add empty sets setting, and you still want to have a reasonable reduction systems, then you need to add this context to solve this problem of empty sets. Okay, so, but you don't need the context. These will be, if these are all non-empty sets, these will be epimorphs. So there will be also no. So what is mean that the model satisfies an equation? So this equation is satisfied if and only if there exists context such that these two morphisms are equal. That's it. And this is all in the symmetric monoidal. But notice we drop the Cartesian case now because there might be multiple different contexts, and therefore there is no context independence there, so we have to drop it. And we call a theory E entails a phi if all models satisfying E satisfy that. Then we say that this logically entails phi in this monoidal category or symmetric monoidal. So this is logical entailment in a given monoidal, symmetric monoidal category. So we are able to. So this is about how how many different. Oh, okay. So okay, the deduction system. So we are able to we have a set of a theory, then we can have the equivalence closure with this kind of closure under monoidal substitution, and this will then I will prove. The point is to prove that this will be a complete, sound and complete system. So then there is a substitution lemma that allows to prove that that this system is sound in any monoidal symmetric monoidal. So anything that you prove with this system will fall in all symmetrical monoidal. And then there is a completion. There is a modified term algebra that we create, and this is, notice we don't choose all the possible terms. We only choose monoidal terms, and we add these garbage elements. Okay, and so this is not the usual Lindenbaum-Tarski algebra. It's a modified version. And then you little bit trickery here used. This is not trivial to be able to define. So it doesn't go through as easily as one might think, but it's pretty easy. It's model, and then you are able to prove this completeness result. Okay, so you are able to prove that in this model something is true if and only it's provable, and therefore we have the monoidal method theorem that if something is true in sets, by completeness there's a syntactic deduction, and by soundness this entailment is true. So we have this. Okay, thank you.
Does this work for like multi-categories as well as mono-categories?
So yeah, that was so we can so I wouldn't. So you can model the language also in this that's a multi-category of sets. But the thing is that it kind of is implied by one of the examples, because you can encode with universal algebra. You can encode enriched multi-categories. So you can have the signature. So you fix a set S, and you can fix a signature. You can add these kind of arrows to M, and then you add these equations. And now a model for this will be an enriched multi-category with elements with a set of objects being S. So and now this allows. Notice that here F there's a changing of position, so the variable symbols are not in the same position. So this is not, you're not able to talk about enriched multi-categories in the setting of monoidal categories, but you are able to define this notion in the symmetric monoidal categories. So now you are able to kind of input all of these things, this language of you are able to kind of kind of code this language of enriched multi-categories inside this multi-sorted universal algebra, and you can, in that way, you can prove things. And then of course you have the B-enriched multi-categories. If the set S is a singleton, you get the enriched operands, and you can add the symmetric things, so you get symmetric operands. So you are able to lift proofs from the set-based settings to enriched settings, depending on that you look at your variables are not repeated in your equations. Yeah.
So maybe I'm misunderstanding slightly, but I think my question is slightly orthogonal. So like you can define what it means to be, or not a monoidal category, not have a model of your signature and a monoidal category, but in a monoidal category.
Yeah, but the idea is that now you can encode all the things you want, and so this is kind of like you have this universal algebra interpret the monoidal category, and then you have this language that describes. You have the theory of, let's say, these multi-categories, and adding that theory to the structure you want, you will get so this is a kind of a it's embedded inside of, so, but I think that you can do it directly. It shouldn't be too difficult, but I'm not sure exactly about the enriched multi-categories. Yeah.
Okay, let's start it again. So
Thanks.
So our next speaker is Aziz Karim from Haifa. He's not here.
He's here.
Sorry, he's not here in person, but he's online. So, oh, and there he is. Hello, Aziz.
Sorry. Yeah, now you hear me now, right?
Ooh, that's not very loud.
Hi. Do you hear me?
Yes, but quietly.
Not good?
I'll see if we can put our volume up. We can go up more. We can go higher. Try now.
Now it's better?
Is that better? Is that good for everyone? Everyone fine with that? That's good. Okay, so you should be able to share your screen when I stop sharing.
Yeah, just a minute. Okay, yeah, now I share you. It's okay?
Yeah, so can I hide this?
Yeah.
Oh, I think that's as good as we're going to get. Okay.
Yeah, my voice is clear. It's okay?
Yeah.
Yes, very good. Okay.
A tiny bit louder.
Yeah, loud is good. Okay, so Aziz is going to speak on homotopical characterization of strong contextuality.
Okay, thank you very much. Thank you for the organizer. I'm sorry that I'm not with you physically. Sorry about this. I couldn't do this. Thank you very much to accept my talk. So yeah, let's start. I will start with experiment in quantum physics. Let's say that we have 3 experiments and we do this 3 experiment together. We're doing this 3 experiment together, and we know that the result of every experiment there is two results can be, okay, plus minus something like, okay, 0 and 1 for every experiment. The good things about this that we can do the 3 experiment together, of course, as much as we want. Yeah, we can do many times a day. But on the other hand, every time we doing this, we can measure just 2 of them. Like we decide, for example, to measure A and B. For some reason for physics, like we can just measure A and B, or B and C, or A and C. We can know the outcome of these 2. We can't know the outcome of the 3 of them every time. But it's good that we can do this many times, so we can get the probability table. Like if we if we measure A and B, we decide like to do this many times and to measure all the time A and B, then we get such a probability table like this. You see, like this. For example, this number tell me what is the probability to get the result to be 0, 0, the outcome 0, 0 when I measure A and B, okay? And this is when the result it's 1, 0, and so on. It's the same for BC, the same for AC. So here we're asking what is the properties of these tables. Of course, this is all non-negative number between 0 and 1, and the sum of this one, the sum of this one, the sum of this one. This is obvious. But the other thing that one can, from this table, to know what is the probability for the experiment A to be 0. One can sum both of these, right? But on the other hand, this actually when we doing this when we measure with B, but we can do this here when we measure with C. Actually, to take from here, like for A to be 0, it's the sum of 2 of this, right? But actually, it's always the same. Like if we really it's the same. So we interested in the case when it's the same. Like we have this property that it's not important, which, for example, I want to know what is the probability when I measure B to be 1, so I can do the sum of this, or I can go here and do the sum of this for B to be 1, okay? It's the same, or 0 or something. So we have these equations. But the surprising thing that even though we did the 3 experiment together every time, and every time we have, actually, if we back here, every time we have three results every time we do this, but we can know just 2 of them. But the surprising thing that we don't have such a global probability table like this, that 3 of this come from them. Because if we have something like this, we expect like we have something like this, and the probability table for 3 of them, because we did the 3 of them together, and the tables come from this table, because, like, for example, I want this, I can sum both of this, like, right? Because it's the case, this is the case when A and B got 0, right? So I can, this is the sum of 2 of this. But mathematically, one can see that some example of such a table that have this property, have these equations, but on the other hand, it's not coming from something global like this. And there is physics experiments like this, quantum physics like this, that it's not coming from probability table. In this case, when it's this table is not coming from such a global table, it's called contextual tables, okay? This kind of table. Okay, but sometimes it's coming, like it's called classic when it's coming from global table, or non-contextual, or classic because it's come from classic physics, like it's not nothing here in quantum. Okay, so how we can describe this using topology? So we can actually draw a triangle that tell me what I can measure together. Like here, I can measure A and B together. I don't see here because of this, right? I can measure A and B together. I can measure B and C together. I can measure A and C together. So I have here actually this probability table, like for this edge between A and B. So what is this? This actually is belong to the distribution NZ2 cross Z2. This is exactly the table I had before. So 3 tables, but also we have also another distribution, for example, for B, what we said, and it's common, like for this and this, right? We said this like in the table before. So we have also distribution in Z2. Okay. So, but we interested in other description, and this description using commutative diagrams. So this is actually the same description, but what we have here, we said, okay, let's put it as one map, 3 of this as one map. Like we have 3 distributions here, right? We have 3 distribution, and we have 3 distribution here. Like this is the distribution when we measure one experiment from this we get. And here, actually, we have what is D0 and D1. It's telling me the faces of the edge, like the point of the initial point and the terminal point of the edge. Like if I taking here this edge, so and I take the terminal point of this edge, which is B, okay, D0, it's give me B, and then this map, it's going to give me this distribution BA, okay. So this is exactly like the distribution BB, sorry, for BB. So this is exactly, if we go into the table, like when we sum this and sum this, this will be distribution for 0 and this for 1. So this distribution on Z2 will be when we sum this and this. But it's the same if we going this direction, like I'm taking DD1. What I mean by DD1 is exactly what I explained now. Like I mean that I have some distribution here in Z22 and I take the column of the, or D0 with this, so sorry, it's not important now, okay, so the column of this, okay, like the column, and this give me a distribution on 0, 1, okay. So actually we have two square here, one for D0, one for D1, so 2 square is commutative. This is exactly to say that we have these equations, okay. Okay, so this actually remind us this kind of things. This remind us what's called simplicial set, which is a basic tool in algebraic topology. It's so important tool in homotopy theory. So let me define what is simplicial set. So simplicial set is a collection of sets with space and degeneracy maps, and xn actually represents the n simplices. So what I mean, like x0, the point. In x0 there is a point. In x1 there is a set that represents what? The edges. And in x2 the triangles, and so on. And there is a face maps like here, like what we have here, D0 and D1, that tell me for every edge, what is the faces of this edge, what is the terminal and initial point for this edge. Okay, these faces maps. And of course, for higher order, like for element in X2, it's a triangle, so there is a 3 faces map, D0, D1, D2, 3 faces map that tell me what is the edges of this triangle, and so on for higher order simplices. There is also the Jersey map. It's not, I will not go into explain this because it's not important for this talk, but it's of course important. I will not ignore this because it's important for the homotopy theory, for the theory which we will use. But for now, let's forget about this. So actually, here is example of simplicial set. Like when I have the 0 simplices is Zn, like n elements, and here Zn cross Zn, and Zn cross Zn cross Zn, the triangles, like, okay, but there is it's obvious what is the faces maps. I didn't draw here the arrows, I forgot. Okay, no problem, but there is like 2 maps to here, which is the faces maps, which is actually deleting, like I delete here or delete here. It's give me 2 faces maps. Here also by deleting, I have 3 choices to delete one of them and to get someone here. Okay, there is the Jersey map is copy by copy. It's not important now, but this actually exactly what we use here, right? This is exactly what we use here, but after applying the distribution monad, right? We're applying this distribution because this distribution is not also in sets, it's in functions. This is actually functor, it's a monad actually even. Okay, so after applying the distribution monad, we got this. So we see like this can be plays a role of the outcomes, right? The outcome space, like we have simplicial sets for the outcome, simplicial sets for the measurement. So because of this, we have the following definition. A simplicial distribution is a simplicial map from some simplicial sets to these simplicial sets after applying like this specific simplicial sets after applying the distribution monad on this simplicial set. Okay. So X is the measurement space. What I mean is the measurement space, because what is X actually? Like in here, like X is as a point, it's is this triangle, for example. The point is exactly the experiment, and the edges it's tell me which experiment I can measure together, right? But it can be more, like it can be something like I have 100 experiment and some 7 experiment I can do together, then and some 8 other experiment I can do together. So I need the higher order simplices, okay? So it can be anything else, not just the example we have. And here this delta Zn is let's see here, sorry. And here delta Zn, it's called the outcome space, because actually it's the n tell me how many outcome I have for every experiment, right? Okay. So actually this in here we encode the probability tables in this simplicial map, okay? Like some experiments and give me some quantum like some statistics from this experiment, and then we can encode all of this in this simplicial map. So all this simplicial map together, actually, if we fix some measurement space, we have fix this n. So all this simplicial map together form a polytope. Actually, it's easy for someone to see that really it's a convex set, because if someone, let me back again, sorry, I'm back too much. But let me back again to this table. Like if someone have such a table that satisfies this equation and have another table that satisfies the same equation, then if someone take quarter of one tables plus the 3/4 of the other tables, will get new tables that really satisfying this equation. It's easy to see. Okay, so it's really a convex set. Like all these such tables, it's a convex set. But even it's yeah, where I arrived here, yeah. But even it's a poly, okay, when x, of course, like we mean here, like x is finitely generated. Okay, in our case, it's like that coming from some experiments. So this is really a polytope. So let me show you what we mean here. There is a picture, but it's just to illustrate what happened. It's not really the real, because it's higher dimension. It can be, it's impossible to draw. But here, what happened, like here, we have all the non-conceptual distribution, the distributions that coming from some global distribution. And here's a contextual distribution. And we are actually interested in this, to detecting such distribution like this. This is what called strongly conceptual distribution. What I mean, why it's strongly conceptual? Because actually this is okay, conceptual distribution, but also we can write someone here as a convex combination with someone in the green, someone non-conceptual. Like here we can, like for example, if I take a point here, I can write here as alpha of this, which is non-conceptual, with 1 minus alpha of this, okay? I can, but here no. So this is called strongly conceptual. Here, strongly conceptual facet, every distribution here, every simplicial distribution is strongly conceptual, okay? Question? There is a question, sorry? Okay, let me continue. So the simplest example when the measurement space is a circle, and with one edge, like when our measurement space is circle, it's not something that coming from, of course, of physical experiments, but it's okay. It's agree with the definition of simplicial distribution. It can be like this, that our measurement space is just a circle with one edge, and the outcome is delta Z2, then really it will be triangles. All that the simplicial distribution, it will be triangle with unique, strongly contextual vertex. Okay, there is just one conceptual. Here is all the classic distribution, all the non-conceptual distribution. Okay, so we will back again a little later to this example. It's important, even if it's not coming from physics, but it's important to understand what happened. So let me go now and explain something about delta Zn, because now actually instead of say that we have n outcome, we replace this by space, by a simplicial set. Okay, for me simplicial, I said space because like it's one can think about it as a topological space, a simplicial set. So topologically, this one is the path in the nerve of Zn. Okay, in the nerve of Zn, which start with some fixed point. All the paths that start with some fixed point. This is the space. As if we think as a topological space, this plays a role of this. So we have a map like from this space to this space, which every path here going to the endpoint. Okay. Here all the path here that start with some point, and here we going this map we're going to the endpoint. Yeah. So this actually helped me to define homotopy between maps, or here null homotopy actually. Yeah. So here is the definition. A simplicial map, if we have a simplicial map from some space X to the nerve of Zn, it's null homotopic if it's factored through this one, from this K map, from this map, okay, or what it's, yeah, okay, from this map. So factorized through this map, it's called null homotopic, this map. Let me explain. There is a picture here. I can explain by this picture. Like, let's say that we have a map from this space to this space. Phi is the map like this, and it's factorized through this. What it's mean? Like we have some map psi that the end point of this is exactly what Phi give me. Yeah. But this actually, what is this? This is a path that started from one point, fixed point, yeah, right? So it's exactly to say that we can go in continuous way from psi to the contents map, right? Because here we have just a contents map all going to this point, okay? So this is exactly what it's meant to be null homotopic. Okay. And now because of that, we have the following proposition. So the proposition says that if we have a simplicial distribution Zn, and if there is subspace of X, subspace of this X, and a simplicial, okay, let me maybe explain it in another way. Like if we down by this, like we have this distribution, simplicial distribution, if we down to the nerve of this using this map, the projection map, yeah, this map, we get actually something like what it's called this deterministic actually. If it's happened, like sometimes we not get, but if it happens that we get something deterministic, what I mean by deterministic, like it's really this from Z to the distribution of this, it's really also, it's a simplicial distribution map, but actually this map, it's 1 and zeros because it's coming from this delta. I mean, this delta that coming from the unit of this distribution monad. So it's just 0 and 1s here. But if it's coming from some map that it's not null homotopic, yeah, not null homotopic, then this P is strongly contextual, okay? This P is strongly contextual. Yeah, I see we are back. Okay. Okay, so then this P is strongly contextual. Is there something with the sound? Everything is okay, George? Yeah, I see something here. Okay. Yeah, you can hear me. Everything is okay. Okay, I will continue. There is a recording anyway, but yeah. Here is in chat. Yes, everything is okay. Sorry about this. I thought maybe something happened. Okay, sorry. Let me continue. So this actually help. This proposition help to detecting some. We drop. Okay. So let me back to this because maybe not everyone heard what I said before. So this helped me to detecting a strong contextuality, because if I have this like some not null homotopic and I can get some P that makes this diagram commute, then it's really we have this P will be a strongly contextual simplicial distribution, okay? But now the question, what is about the opposite direction? Is every strongly conceptual distribution, it's coming from such a thing that for every strongly conceptual distribution, there is a not null homotopic map that makes this diagram commute? This is the question. And no, it's not true actually, but it's true for when we're talking about when n is two outcome, as we started from the beginning, our experiment, and also when x is one skeleton, like we have just, we can measure two together, two experiments together, every two, like as we have before, like, but we can have more, but we can do, it's actually includes many examples, many important examples. So in this example, really, it's the opposite direction. It's true, and let me explain why it's true. So to do this, actually, here we use category theory. So let me go into here. We define a compository. Actually, we not define, it's defined before in the paper of compositories and glyphs for Flory and Fritz. What is a compository? Actually, it's a simplicial set, but where there is some higher order compositions, like if we take some M simplex and N simplex that have common K simplex, like the end of this M simplex is the beginning of this N simplex, then we can get in higher order simplex, M plus N minus K simplex, where this is the composition of them. Like there is one like this, not like we can feel by, no, there is one like this, there is a composition operation, and this composition operation have nice properties. Like for example, associativity is associative. Actually, there is some axioms for this, not including associative, but the nice thing is that they get associativity from this. So this is a nice composition. An example of this, which is really trivial example, like the nerve of category. The nerve of category, if one thinks like we have two simplex nerve of category, maybe I can write here. And other one like three, and then really which have common here one. So we rightly can think directly, we can think about this to be four simplex, okay, in the nerve of the category. But actually, the interesting thing is that if we apply the distribution monad in the nerve of a category, this also still give me compository, which is not trivial compository. And what I want to show you is that this outcome, like D of the outcome space, is really compository of our outcome space. Why is this? Because actually this delta of Zn actually is the nerve of this category. This in the case of Z2, but one can do this in the case of Zn in general, okay? But in the case of Z2, this is delta Z2 actually is the nerve of this category. Okay. So now actually the composition that we need for this talk actually from the compository, when we have some in D of delta Zn, what we need when we have some distribution and other distributions, then we get this composition in the compository that it's like 1 plus 1 minus 0. This is 0, so it's it's feel like a two simplex. But we need this when we marginal this in this edge, okay? And this is our composition of probability. We compose probability. And because of that, if we have X is one skeletal, like directed graph, I mean by one skeletal, okay? That's we have just edges and we don't have triangles on this, then we can think about the simplicial distribution as a category because of this composition. We can take all the composition, and if we have such also the direction, like if we have such a map, we can such a distribution from here to here. We can think about there is also the like some transpose of this from this point to this point. Okay,
We're wrapping up.
I still have 2 or 3 minutes, or
So yeah, we're just wrapping up now. So it's already 4:30.
yeah, it's recorded and everything is okay. Or sorry.
We're just, it's time to finish off. Yeah. I'm just.
Yeah. Okay, I should continue.
Just for like a minute or so, just to come to.
I'm not here too good, sorry.
Can't hear you. Can't hear me. Just just for 1 minute or so.
Yeah, okay. I will continue for a minute. So let me maybe say this important proposition and then we finish. So the important proposition about this category that is a strongly conceptual. It's depend only in the what calls endomorphism here, like from one point to itself. This is an important thing. So something is strongly conceptual if there is one point such that the distribution here, there is some distribution here, which is strongly conceptual in one edge circle. We say that this is example before, like when we have one edge circle, then we have just unique. Okay, where I can find it. We have just unique strong conceptual. Yeah, so this is the case. Like we have this is strong conceptual if and only if there is really distribution like coming from these all compositions on the one edge circle that it's a strongly conceptual. And from this we can prove the opposite direction. Like really this is will be off and only if in this case of course, like in this case when we have two outcomes and the one skeletal measurement space. Yeah, so that is this finish. Okay, thank you.
Thank you.
I'm sorry, I'm also not hearing you very good. Like it's also the what happened? It was disconnecting or something through the talk or
Maybe just one quick question.
yeah. Okay.
Okay. Well, can I just check? Just to get the broad picture. So the note is it the case that the notion of strong contextuality is like something which is already known, but the new thing is, but the homotopic characterization is new. Is that
yeah, right. Yeah, it's defined before. Yeah, of course, it's defined. I think the first time, I'm not sure about this, but at least in 2011, 2010, like there is a paper for Abramsky and other about shift theoretic approach to conceptuality, something like this. So it's mentioned there. I think this is the first time it mentioned. Maybe before, I don't know, but yeah, it's yeah.
Okay, thanks.
Yeah, you're welcome. You're welcome. Okay, thank you very much.
Share screen, big. I think this one should just work. Like that. Right that there. So that.
And I'm pointing
Down goes forwards.
down goes forwards, up goes backwards.
Yes.
Okay, thank you.
Okay, so our last talk of the session is by Joshua Wrigley, who will be at Queen Mary as of next week.
Yes.
And he's going to speak to us about the topos theoretic framework for reconstruction theorems in model theory.
Brilliant. Thank you very much for having me. Downwards goes forwards. There we go. So the type of reconstruction theorems I want to talk about are like these. So this is a very classical result in model theory, which says that whenever we have countable models of an omega categorical, that means that their theory, they are the unique countable model for their theory, then their theories are determined by their topological automorphism group. And they're determined up to bi-interpretability. So this is a notion of equivalence that you find in model theory. And this is very nice, and people have gone very far with this. But today we want to sort of think about how we might generalize this type of result. So what, if we remove the assumption that M and N are countable models, we're going to have to weaken our homeomorphism condition on the topological groups. And if we remove the atomicity, which is equivalent to omega categoricity assumptions on our theories, then we're no longer going to be able to use topological groups. We're going to have to generalize from topological groups to something else, and that will be topological groupoids. Just to mention that there is work in this direction in the model theoretic literature. Just recently, Ben Yakov has constructed a groupoid out of a theory which determines theories up to bi-interpretability in the classical context. But the point is that his groupoids that he constructs are a model theoretic construction. They are not, the underlying groupoids are not groupoids of models. So we're not going to get particularly the same type of flavor. And that's where this work comes in to make sure that all of our groupoids are always groupoids of models. It's going to make the condition a little bit more complicated, but we're going to have the same kind of flavor. So the theorems that we're generalizing look like we have some combination of topological and algebraic structure on one side, and then some logical structure on the other side. And the way we're going to generalize those type of theorems is by sticking a topos in the middle, and then going, look, my topological algebraic data is generating my topos. My topos is represented by this logical data, and then I'm going to ask when those two things are equivalent. And this is going to form the template for our reconstruction theorems. So how do you get a topos out of some topological algebraic data? If we started with a category, then I'm going to say that a bundle over that category consists of some map down to the space, to the set of objects of my category, and we're going to have a lifting of the action of the arrows onto the fibers. So this is the same thing as being a discrete bar vibration. And when that category has some topological data, when it's a topological category, we're going to say that such a bundle is a sheaf if this map from Y to the set of objects is a local homeomorphism and this action is continuous. The morphisms of sheaves we're going to consider are those where they are continuous maps of the sheaves and they respect the action by the arrows of our category. And when we take the category of sheaves and their morphisms together, this gives us a topos. So this is how we go from topological data to a topos. In the other direction, if we had, some examples first to give you all of the idea. We can take a categorically discrete category where all of the arrows are just the identity arrows. And this just gives us the usual notion of the topos of sheaves on a space. We could also take the topological group, consider that as a one-object topological category. When we perform this construction, we get the topos of continuous actions by that group on discrete sets. So that's just two examples to mull over. We also have a logical description, which is given by this idea of the classifying topos. Now, the idea of the classifying topos is that the morphisms that we're going to consider, the geometric morphisms between toposes, are the same as models. So the category of models of our theory and sets is equivalent to the category of geometric morphisms from sets to our classifying topos and natural transformations between these. And we can say that we want this to hold naturally for all toposes, and there's a notion of how to have a model internal to another topos. And this defines our classifying topos up to equivalence. Moreover, every geometric theory has a classifying topos, and every topos has a classifying topos of some geometric theory. So as an example, we had some classical propositional theory, and we took its stone space of models, and the sheaves on that stone space is going to classify our theory. So with that definition in mind, we're going to say that two theories are Morita equivalent if they have naturally equivalent categories of models in all toposes. And this is the same thing as saying that they have equivalent classifying toposes. We're going to replace bi-interpretability in this discussion of model theoretic reconstruction theorems by Morita equivalence, just because it covers all of the pathological cases that might crop up. So if two theories are biointerpretable, then they're going to be Morita equivalent. The opposite implication doesn't always hold, but in those counterexamples you can construct, they really should be equivalent, the two theories. And indeed, if we have, whenever we're in like a fairly classical context, we've got negated equality and more than one element in our model, then biointerpretability is the same as Morita equivalence. So that describes how we're getting logic into topos theory. And now let's have some examples of the type of reconstruction theorems we can build using this framework. So we can get the classical Albrandt-Ziegler type result by using this fact from topological Galois theory that if we've got a complete omega categorical theory and we've got a countable model for that theory, then the topos of continuous actions by the topological automorphism group represents the classifying topos of the theory. That is, a classifying topos is equivalent. And so now it just immediately follows that if we have two theories, T1 and T2, complete omega categorical theories, they're going to be Morita equivalent if and only if these toposes of automorphism actions are equivalent. And now we have to use the fact that these were countable models. We can do a back and forth argument and have that these two toposes are equivalent if and only if the topological automorphism groups are homeomorphic. And so we can recover the classical Albrandt-Ziegler result. That's why we need countable models, because if we didn't have countable models, that last implication would double implication would no longer hold. Another example would be classical stone duality. If we had a propositional theory and we knew already that the classifying topos of that theory is the sheaves on its stone space, well then look, our two theories are Morita equivalent if and only if we go down to the toposes, and we know that in the case of sober spaces, the sheaves or over sober spaces are equivalent if and only if the sober spaces are actually equivalent. And so we get stone duality. Now, the groupoidal extension I want to talk about today has a very similar form. We have a topological groupoid, we get a topos of equivariant sheaves over that groupoid, and we know that for certain representing groupoids of models of our theory T, we can find a representation of our classifying topos by that topological groupoid. And so now we have our chain of equivalences, that T1 and T2 are going to be Morita equivalent if and only if the topos of sheaves on these representing groupoids are equivalent. But then what happens next? What's the next double implication? And that's a little bit difficult in what I want to get onto today. So to have a quick overview, I'm going to talk about when we have representing groupoids. I'm going to hopefully fly through that a little bit quickly because I talked about it at other conferences. And then the new stuff I want to talk about today is what goes here in place of this question mark. Okay, so the first theorem we need is a characterization of when we have a representing groupoid of models. And it actually turns out there's only two conditions you need to check. You need to check that the groupoid of models is what's called conservative. That's a fairly standard notion in logic. And then the second notion, which is not so standard, is this idea of elimination of parameters. So I'll explain what's going on there. So yes, I'm going to define elimination of parameters, and then I'll restate the theorem so that everybody knows it. Okay, so the idea of parameters is if we have a model, then we can parameterize the elements of those models by some set living elsewhere. Now, I've stated that in a very model theoretic manner in terms of expanding the signature by constant symbols and interpreting those symbols. Perhaps it would make more sense for this audience to think about it as we have a set of parameters and our model admits a partial surjection from that set. And when we have such a parameterization of our model, we can talk about definable subsets in our theory, not just in terms of subsets of the models defined by a formula, but now where those formulas involve parameters from our parameterization. The same thing's going on when we have groupoids. So if we have a groupoid of models, we can index all of the models in our groupoid by some shared set of parameters. And now we have definable subsets, which are going to be the set of pairs of tuples inside that model plus the model, which satisfy that formula. And we can do the same again with parameters being involved. Now that we've got that out of the way, we can talk about what it means to eliminate parameters or how we interpret formulae. So let's just assume that we're working over a single sorted field. And for each n, we've got some bundle where we take the n tuples in our model and we project down onto the model in our groupoid of models. And if we have a definable, if we have a formula, we can take the subset defined by that formula of all of the tuples that satisfy that formula. And then we note that this subset is stable under the action, and that's because these are isomorphisms of models, and so they have to preserve the interpretation of the formula. So I mean stable in that if you start inside the subset, you apply the action, you're going to end back inside the subset. We could also take definables with parameters, subsets satisfying formula involving parameters, but now this is no longer a stable subset. The reason is that these isomorphisms only preserved the structure of our signature. They didn't have to preserve any of the interpretations of the parameters. But we could always just take the isomorphism closure of this definable with parameters. And in the particular visualization I've given you here, you'll notice that these two sets line up and the isomorphism closure is equal to the interpretation of the previous formula phi. And we take that as our definition of elimination of parameters. That is, we've got a groupoid, some indexing by parameters, then for every formula involving parameters, the isomorphism closure of its interpretation is definable without parameters. And that's enough to give us a characterization of when our classifying topos is represented by an open topological groupoid. That is, the source and target maps are open as well as continuous. So the two conditions we need is conservativity. That is, the two formulae are interpreted identically in all of our models, or they may have to be provably equivalent in the theory. And the second condition is this elimination of parameters I just described. So have a look at a few examples of when this occurs. We recover the previous representation theorems found in the literature of Butz and Mordijk and Alde and Forsey, involving taking this huge groupoid of all of the indexed models for some sufficiently large set of parameters, or all of the enumerated models for a sufficiently large set of parameters. We also recover the Caramello results I cited earlier, which is whenever we have an atomic theory, which is the same as saying it's omega categorical, then the automorphism group of that model eliminates parameters if and only if that model is ultra homogeneous, which is saying that finite partial isomorphisms extend to total isomorphisms of the structure. And that's how we used it earlier in order to get the fact that for our omega categorical theories, they're represented by the countable models of the theory, because countable models are always the countable model of an omega categorical theory is always ultra homogeneous. Okay. So now we know when our classifying topos is equivalent to the sheaves on a topological groupoid, The next question, in order to finish that chain of equivalences, is when do we have that two toposes of sheaves on groupoids are equivalent? That is what is a characterization of Morita equivalence for topological groupoids. And we're going to recover this characterization as a consequence of this biequivalence that I want to prove here. So in this biequivalence, this topos ISO WEP, that is the bicategory of toposes with enough points, and all geometric morphisms between them. And then as our two cells, we're taking the natural isomorphisms between these. Log groupoid is going to be a full two subcategory of the category of topological groupoids, which I'll define in a sec. And then this fancy W is going to be a bicalculus of left fractions on this category log groupoid. And so in this part B, I'm going to compare. So we're localizing on the left rather than the right, which if there are any topospheres in the room, localizing on the right is maybe the more classical thing to do. I'll explain why that's not possible in this context. Then I'll define the bicategory of logical groupoids. I'll give a description of the weak equivalences. We'll restate the biequivalence and then conclude with our groupoidal extension of Albright-Siegler. So just to begin by defining, so that everyone's on the same page when I say category of topological groupoids, a homomorphism of topological groupoids is just going to be a continuous functor. That is, the action on objects and the action on arrows is continuous with respect to topologies. And a transformation is going to be a natural transformation where the map which sends an object to its component is also continuous. And all of that data together defines a bifunctor, sheaves from topological groupoids, and if two toposes, but it factors through this bi subcategory of toposes with enough points and natural isomorphisms. I mentioned the sort of classical literature earlier in topos theory. About localizing on the right. This is due to Mordyke, and remember bicategorical details were added in a paper by Kronk. There is this biequivalence between a localization on the right of a subcategory of here, very carefully, this is localic groupoids. So 0.3 topology going on here. We're taking the 0.3 version of a topological groupoid. And we're localizing on the right. And this is a very nice result. The original intention was try to recreate this, but it turns out that it's never possible to localize on the right and get a biequivalence. It's quite a nice proof, so if you indulge me, I'm going to do it now. There is quite a glaring typo because it's a proof by contradiction. We're not supposing our hypothesis. I forgot to take out the not. So suppose that we do have an equivalence between topos WEP ISO and some localization on the right, a subcategory of topological groupoids. Well, then we'll take some topos contained on the left, which has enough points, but it has a large set of points. So an example would be the classifying topos of groups. There's an unbounded number of groups, but it has enough points all of the same. Let's pick some representing groupoid contained in our subcategory C. And by assumption, there exists a point which is not contained in the space of objects for this groupoid. Now, by the assumption, again, this should be an equivalence, that we have this biequivalence, then there exists a homomorphism contained in our category C, which is inducing this point P. But because of that, it means that any section of this, of the unique geometric morphism from sheaves on Y0, that is a space of objects of Y to sets, any section of this would yield a factorization of P through this morphism sheaves of X0 onto E. And that contradicts our assumption that P was not contained in the set of points X0. So that means there is no section of this unique geometric morphism, which means that this is the empty space, which means it's topos of sheaves is the trivial topos. But then we have a surjective geometric morphism onto sets from a trivial topos, i.e. sets is the trivial topos. And I hope everybody here agrees that if your category of sets is the trivial category, something's gone wrong. And so this is the contradiction. And so then we never have a bioequivalence here. So that's why we're localizing on the left. The category of topological groupoids we're considering is this category of logical groupoids. It's the full subcategory of all open topological groupoids, where the spaces involved are sober, and it has this property of being a tau complete in the sense that the space of arrows has all of the topospheritic isomorphisms going on. So whenever we have an isomorphism between the points, that's instantiated by an arrow in our topological category. And also the topology on our space of arrows is the coarsest possible topology with respect to that data. The reason I'm calling them logical groupoids is because it is the it's equivalent to being a groupoid of models for a theory classified by its topos of sheaves with all of the possible isomorphisms between those models. And then there's a sort of correct choice of topology that you should be taking, which satisfies these conditions. The weak equivalences, on the other hand, involve a homomorphism of logical groupoids where it's the inclusion of a full subgroupoid such that we have this condition, and I'll chat about maybe why this isn't such a satisfactory condition at the end, that for any choice of a theory classified by the sheaves on W, that means W can be viewed as a groupoid of indexed models for the theory, then the subgroupoid Y, which will also be a groupoid of indexed models, is still conservative and still eliminates parameters for that theory. So let's denote the class of weak equivalences by W. It's a corollary of the classification result theorem A we had earlier, that these weak equivalences induce equivalences of toposes. And we can also prove that every geometric morphism is induced by a co-span of homomorphisms of these groupoids. That is, we've got a homomorphism here to W, and then this homomorphism here is a weak equivalence. So that means when we apply the topos of sheaf functor to this, sheaves on phi is going to be equivalent to F, and this is the equivalence to sheaves on Y. And then when we plug all of that together, we get our biequivalence results. Just to remind anyone who hasn't come across these localizations before, the objects are still logical groupoids, the arrows are co-spans, and the two cells are transformations between the legs of our co-spans. And so as a consequence of that, we deduce that whenever we have two logical groupoids, they are Morita equivalent if and only if there is a co-span of weak equivalences. And therefore, if we have two theories with representing groupoids, those theories are Morita equivalent if and only if their representing groupoids admit a co-span of weak equivalences. So I'll just briefly mention some future directions for where this work could go. What sort of properties are being preserved by weak equivalences? That's a very interesting idea, especially given all of the model theoretic literature there is on countable models for omega categorical theories. And then the description I've given isn't particularly satisfactory, and there's this sort of oracular choice of theory classified by your topos. But really that choice of theory is just saying, pick a nice set of sheaves for this topos. Pick a nice set of objects of your topos. So maybe there's a entirely topological description out there, which will simplify what's going on. I'll leave you with some references. Thank you very much for listening to me.
Okay, thank you, Joshua. Questions?
Just out of curiosity, I wouldn't say that I understand the what from the whole. I found it very fascinating. The question is, can we gain something for finite models here?
That's a very interesting question. Because as you know, finite model theory has a very different feel to classical model theory. I would hazard a guess, and this is very much a shot in the dark, that this has more of a flavor of classical model theory, and potentially doesn't have as much to say in its current form about finite model theory. It's the sort of next steps that I'm pursuing have parallel classical model theory a lot more than anything on the finite model theory side. Yes, the issue there is that in order to have the groupoid representation results, you need your base topos to have a natural number object. So there is potentially a way of getting around that, but just as in terms of applying the traditional literature, you need to be working in something with infinity involved.
This difference between Morita equivalence and by interpretability, I mean, do you think there could be some scope? You said they're not the same, although they are in a lot of cases. Do you think there could be some scope for getting something from by interpretability? Is that just something you wouldn't want to do?
So the issue with getting by interpretability is that Morita equivalence involves taking, so if we go all the way back up to the first slide, I think that's where the notion of interpretability is. I'm sorry, maybe if I click here, that will be quicker. So here we have a definable quotient of definable subsets is the idea of being interpretable in another structure. Morita equivalence is the same, except now that it's allowed to be a co-product of definable subsets. And so that's the only distinction. And so in the classical context, you're able to construct co-products, or disjoint co-products, importantly, out of definable subsets. But if you're working in straight geometric logic where you don't have a complement for equality, that's where the distinction comes in. So for any application that classical model theorists would care about, there is no distinction. It's just a case of being absolutely correct, but we're not leaving any pathological cases.
Is this this notion of eliminating parameters? Is this a model? Is this considered a model theory?
It feels very model theoretic, but I haven't seen it in the literature. It was involved in coming up with this classification result, like things like ultra homogeneity is used all over the place, but elimination of parameters in particular, I haven't come across before. But it also emulates a lot of conditions out there. It's not exactly equivalent, but it looks like.
Okay, let's thank Joshua again.
So yeah, that's the end of today's talks. So those of you coming to the dinner later, at 6 o'clock, we've got the room from in Cherreds. The details are all on the website how to get there. So you can mill around here from here, so you can go off and do whatever you want. But we'll see those who come to dinner, 6 o'clock in Cherreds.
It is close by.
It is in the centre, so yes, you need to get the train to the station. Or you can walk, but it might start raining. Walk by the canal is nice, if you like to. You are right, right?
Yeah, that was fast.
That's really bad. Yeah, I heard this. I heard there was a couple of parties doing gymnastics.
Yeah, it like seriously,
We're gonna start about this.
So who wants to walk?
I saw you do
You don't look like you're in something like
I think it's realized it's a fire.